Welcome! In this session, we'll dive into LeetCode problem number 1895, largest magic square. This is an exciting problem that challenges us to find the largest square subgrid in a given matrix where the sums of all rows, columns, diagonals, and anti-diagonals are equal. We'll explore the problem step by step and break it down into manageable parts. Let's get started. A magic square is a square subgrid where the sums of all rows, all columns, and both diagonals are equal. In this problem, you are tasked with finding the size of the largest magic square within a given M by N grid. The grid is represented as a 2D integer array, where each element corresponds to a value at a specific row and column. The size of the grid can be as large as 50 by 50, and the values in the grid can range from 1 to 1 million. Your goal is to output an integer, which represents the side length of the largest magic square found in the grid. Let's look at some examples to understand the problem further. In the first example, the input grid is a 4 by 5 matrix. The largest magic square that can be found in this grid has a size of 3 by 3. The subgrid that forms this magic square is shown here, with the values 5, 1, 6 in the first row, 5, 4, 3 in the second, and 2, 7, 3 in the third. For this subgrid, the sum of each row is 12, the sum of each column is 12, and the sums of both diagonals are also 12. Since all these conditions are met, this subgrid qualifies as a magic square. Therefore, the output for this example is 3, which is the side length of the largest magic square. Now, in the second example, the input grid is smaller, with dimensions 3 by 4. Here, the largest magic square has a size of 2 by 2. The subgrid that satisfies the magic square conditions contains the values 3 and 3 in the first row and 3 and 3 in the second row. In this subgrid, the sum of each row is 6, the sum of each column is also 6, and the sums of the diagonals are 6 as well. Since all criteria for a magic square are met, the output for this example is 2, representing the side length of the largest magic square. There are some key constraints and considerations to keep in mind for this problem. If the grid has only one row or one column, the largest magic square can only be a single cell, as no larger subgrids are possible. Additionally, because the grid values can be very large, brute force solutions that check every possible subgrid will be inefficient. Instead, the solution needs to focus on optimizing the search process to handle grids of up to 50 by 50 efficiently. Also, the size of the largest magic square cannot exceed the smaller of the two dimensions, M or N, since it must fit within the grid. To solve the problem of finding the largest magic square, we first need to understand the requirements. A magic square is a square subgrid where the sums of all rows, columns, and both diagonals are equal. The brute force approach is the most straightforward way to tackle this. In this method, we systematically check all possible square subgrids within the given grid. For each subgrid, we calculate the sum of every row, column, and diagonal, verifying if they match. Starting with the largest possible square size and working downward, we aim to find the largest square that satisfies these conditions. However, this approach has a significant drawback: its computational cost. Checking all subgrids for larger grids quickly becomes inefficient, with a time complexity of O, M times N times K squared, where K represents the side length of the square being tested. This makes the brute force method impractical for grids with large dimensions, leading us to explore more efficient strategies. To improve upon the brute force method, we can use an optimized approach based on prefix sums. The prefix sum technique enables us to calculate the sum of any row, column, or diagonal in constant time, eliminating the need to recalculate sums repeatedly. First, we pre-compute the prefix sums for all rows, columns, and diagonals across the entire grid. Then, we iterate through all potential top left corners of square subgrids and test different square sizes. Using the pre-computed prefix sums, we can quickly determine whether the row, column, and diagonal sums are equal for a given subgrid. If these conditions are met, we track the size of the square and continue searching for larger valid squares. This optimization reduces the time complexity significantly, as pre-computing prefix sums takes O, M asterisk N, and testing all subgrids for each square size is approximately O, M asterisk N asterisk K. In addition, we can incorporate further optimizations, such as stopping early when a valid square is found or ruling out subgrids that cannot possibly form a magic square based on their structure. These enhancements make the solution even more efficient. The chosen strategy for this problem is the optimized approach using prefix sums due to its balance between efficiency and clarity. While the brute force approach is conceptually simple, its high computational cost makes it unsuitable for larger grids. By leveraging prefix sums, we eliminate redundant calculations and achieve a more scalable solution. The key insight here is that prefix sums allow us to retrieve the sum of any row, column, or diagonal in constant time, which directly addresses the inefficiencies of the brute force method. Additionally, starting with smaller square sizes and expanding ensures that we only consider valid magic squares, avoiding unnecessary checks. While alternative strategies, like early stopping or bounding conditions, can further improve performance, they add complexity to the implementation. The prefix sum approach strikes the right balance, making it practical for grids of all sizes while adhering to the problem's constraints. This method provides both clarity in implementation and efficiency in execution, making it the optimal choice for solving the largest magic square problem. The problem we're solving involves finding the largest square subgrid within an MXN grid where the sums of all rows, columns, and both diagonals are equal. This is known as a magic square. The challenge here is to efficiently verify these conditions, especially for large grids, while keeping the algorithm optimized. To achieve this, we first pre-compute prefix sums for both rows and columns. The idea behind this is that, in a magic square, the sums of rows, columns, and diagonals need to be calculated repeatedly, and recalculating these sums for each subgrid would be computationally expensive. Instead, by leveraging prefix sums, we can calculate cumulative sums of rows and columns just once and reuse them. Specifically, we create a 2D array called rowSum, where each entry represents the cumulative sum of elements in a row up to a specific column. Similarly, we create colSum, where each entry represents the cumulative sum of elements in a column up to a specific row. This pre-processing step significantly reduces the amount of redundant computation as we move forward. Once we have the prefix sums, we proceed to iterate over all possible square subgrids. To optimize this, we start with the largest possible square size and work our way downward. This way, as soon as we find a valid magic square, we can terminate early without needing to check smaller squares. For a square of size k, we iterate over all possible top left corners of the square, denoted as I, j. After identifying a candidate square, we need to verify its magic square properties. Using the pre-computed rowSum array, we can check that all rowSums within the square are equal. For any row R in the square, the sum can be computed efficiently using the difference of prefix sums. Similarly, we use the colSum array to verify that all column sums are equal. For any column C, the sum can also be derived using prefix sums. Finally, we directly compute the diagonal sums, as these cannot be pre-computed. For the main diagonal, we traverse from the top left corner to the bottom right, and for the anti-diagonal, we traverse from the top right corner to the bottom left. If all these conditions are satisfied, we have a valid magic square. After checking all possible squares, we return the size of the largest one found. Let's highlight some key insights that make this approach efficient. First, prefix sums are a game changer here, as they reduce the time complexity of row and column sum calculations from OK to O1 for any subgrid. This optimization is crucial when dealing with larger grids. Second, starting with the largest square size and working downwards allows for early termination as soon as a valid magic square is found, saving unnecessary computations for smaller sizes. However, diagonal checks remain OK per square because diagonals cannot be pre-computed in the same way as rows and columns. To implement this approach effectively, we rely on data structures such as the prefix sum arrays rowSum and colSum, which store cumulative sums for rows and columns respectively. These arrays eliminate redundant calculations during the magic square verification process. In terms of complexity, the pre-computation step takes M*n time to build the prefix sum arrays. Iterating through all possible square sizes, top left corners, and performing diagonal checks results in a complexity of O(min)(m)n(3). Combining these, the overall complexity of the algorithm is O(m*n plus min)(m)n(3). This balance of pre-processing and efficient iteration ensures a practical solution even for larger grids. Finally, let's address some important edge cases. First, a 1x1 subgrid is always valid, as a single cell inherently satisfies the magic square conditions. Second, if no magic squares exist within the grid, we simply return 0. Third, for non-square grids, we must ensure that our iterations respect grid bounds to avoid accessing invalid indices. Lastly, we need to handle cases where the largest magic square aligns with the edges of the grid. For example, if the bottom or right boundary of the grid coincides with the square's edges, we must ensure that all computations, including diagonal checks, remain within the grid's valid range. Accounting for these edge cases guarantees the robustness of our algorithm across all possible inputs. Here, we start by defining the function largest magic square inside the solution class. The first step is to determine the dimensions of the grid, m and n, which represent the number of rows and columns, respectively. Next, we pre-compute prefix sums for both rows and columns to make the calculations more efficient later. The row_prefix array stores cumulative sums for each row, while the col_prefix array does the same for each column. These prefix sums allow us to calculate the sum of any subarray in constant time. The nested loops then populate these arrays by iterating through each cell in the grid, updating the cumulative sums for both rows and columns based on the current cell value. After the setup, we define the helper function is_magic, which will be used to determine whether a specific subgrid forms a magic square. The function starts by calculating the target sum, which is derived from the sum of the first row in the subgrid. This target will be used to validate all rows, columns, and diagonals of the subgrid. To begin this validation, we iterate through the rows of the subgrid and ensure that each row's sum matches the target. If any row's sum deviates, the function immediately returns false. Similarly, we check the columns by iterating through each column in the subgrid and verifying that their sums match the target. If any column check fails, the function also returns false at this point. Once the rows and columns have been validated, the function proceeds to check the diagonals of the subgrid. For the main diagonal, we initialize a diag_sum variable to 0 and iterate through the diagonal elements by incrementing both the row and column indices simultaneously. The sum of these elements is calculated and compared to the target. If the diagonal sum does not match the target, the function returns false. Similarly, for the anti-diagonal, we initialize an anti_diag_sum variable and iterate through the elements by incrementing the row index while decrementing the column index. The sum of these elements is computed, and if it doesn't match the target, the function again returns false. If all checks pass, the function finally returns true, confirming that the subgrid is a magic square. To find the largest magic square, we iterate through all possible square sizes, starting from the largest size down to 1. For each size, we check all potential top left corners of subgrids within the bounds of the grid. If a valid magic square is found, its size is immediately returned. If no magic square larger than size 1 is found, the function returns 1 as the default. This ensures we explore all potential configurations efficiently while adhering to the problem constraints. To solve the problem of finding the largest magic square, we begin by importing the necessary libraries and defining our solution class. The main method here is largest magic square, which takes a 2D grid as input. First, we determine the dimensions of the grid using M4 rows and N4 columns. Next, we pre-compute prefix sums for both rows and columns. These prefix sums help us efficiently calculate sums for any subarray within the grid. Specifically, row prefix stores cumulative sums for each row, while col prefix does the same for columns. The nested loops iterate through every cell in the grid to fill up these prefix arrays. Additionally, we define a helper method is_magic to check whether a square of a given size, starting at a specific top left corner, satisfies the magic square properties. The first check within this method ensures that all rows in the square have the same sum. This is accomplished by comparing the sum of each row to a target value, which is derived from the prefix sums for the first row of the square. Once we verify the row sums, we move on to check the columns of the square. Using the column prefix sums, we calculate the sum for each column within the square and compare it to the target. If any column fails this condition, the square is not magic. Next, we verify the main diagonal of the square. To do this, we iterate through the diagonal elements, summing up the values from the top left corner to the bottom right corner. If the diagonal sum does not match the target, the square is disqualified. Similarly, we check the anti-diagonal, which runs from the top right corner to the bottom left corner. As with the main diagonal, the sum of these values must equal the target for the square to qualify as magic. If either diagonal check fails, the method returns false, indicating that the current square does not meet the requirements of a magic square. Finally, the method returns true if all the conditions for a magic square are satisfied. In the main function, after defining the helper method, we proceed to test all possible square sizes, starting from the largest possible size and working downward. This ensures that we find the largest magic square first. For each square size, we iterate over all possible top left corners within the grid that can accommodate the square. The helper method isMagic is invoked for each candidate square. If a valid magic square is found, we immediately return its size. If no magic square larger than 1 times 1 is found, the function defaults to returning 1, as every individual cell in the grid qualifies as a trivial magic square. This completes the implementation, providing an efficient way to solve the problem by leveraging prefix sums and systematic checks for the magic square properties. Here, we begin by exploring a 3x3 grid to understand how the algorithm identifies the largest magic square. First, we compute the prefix sums for both rows and columns. The row_prefix array holds the cumulative sums for each row. For example, the first row's prefix sums are 0, 7, 8, 12, where each value represents the sum of elements in that row up to the respective column. Similarly, col_prefix captures cumulative sums for each column. For instance, column 1's prefix sums are 0, 7, 9, 12. With these prefix sums pre-computed, we can efficiently check subgrids of various sizes. Starting with a size of 3, the algorithm tests whether the entire grid forms a magic square. This involves checking if all row sums, column sums, and diagonal sums match a target value derived from the prefix sums. Now, focusing on the 3x3 grid, we evaluate the top left corner at 0, 0, with a target sum of 12, calculated using the prefix sums for the first row. The algorithm verifies that all row sums and column sums are indeed 12, but the main diagonal sum is 14, which invalidates the square. Next, we reduce the size to 2 and test the top left corner again. For a 2x2 square, the target sum becomes 8. The rows, columns, and diagonals all sum to 8, confirming this subgrid as a magic square. Thus, the largest magic square in this grid has a size of 2. The final output for this example is 2. In the second example, we analyze a wider grid with dimensions 3x5. As before, we start by pre-computing the prefix sums for rows and columns. For instance, the first row's prefix sums are 0, 1, 3, 6, 10, 15, and the first column's prefix sums are 0, 1, 7, 18. These cumulative sums allow us to quickly assess subgrids of different sizes. Testing begins with a size of 3, starting at the top left corner, 0, 0, and using a target sum of 6. However, the row sums do not match this target, rendering the square invalid. The algorithm then shifts to the next possible position, 0, 1, with a new target sum of 9. Again, the row sums fail to match, confirming that no 3x3 magic squares exist in this grid. After failing to find a valid 3x3 magic square, the algorithm tests smaller subgrids. For a 2x2 square at the top left corner, 0, 0, the target sum is 3, derived from the prefix sums. This time, the rows, columns, and diagonals all satisfy the magic square condition, making this subgrid valid. The largest magic square in this grid is therefore 2x2, and the output is 2. This example illustrates how the algorithm systematically tests subgrids of decreasing size until a valid magic square is found or all possibilities are exhausted. In the final example, we consider a single-cell grid with the value 5. The prefix sums for both rows and columns are simple, row_prefix equals 0, 5, and col_prefix equals 0, 5. Testing a size of 1, the target sum is 5, which matches the single value in the grid. Since there are no other rows, columns, or diagonals to check, the algorithm concludes that this grid is a magic square of size 1. This edge case demonstrates that any 1x1 grid is inherently a magic square. Summarizing the examples, we saw how the algorithm identifies magic squares in grids of varying sizes, handles edge cases effectively, and outputs the size of the largest magic square found. The time complexity of the solution is O, m asterisk n asterisk min, m, n, asterisk asterisk, and we can understand this by breaking it into its components. First, we have the pre-computation step where we calculate prefix sums for rows and columns. This involves iterating through every element in the grid, so this step alone contributes O, m asterisk n, asterisk asterisk. Next, we consider the outer loops where we try all possible square sizes, starting from the largest possible size, which is min, m, n, and working down to 1. For each square size, we calculate all possible starting positions for the square in the grid. The total number of valid positions across all square sizes sums up to O, m asterisk n, asterisk asterisk as well, due to the arithmetic nature of the decreasing dimensions. These two steps lay the foundation for the overall complexity. Now, let's analyze the magic square check, which is the core of the algorithm. For each subgrid of size x size, the is_magic function verifies if the square is magic. This involves row and column checks, each taking O, size, time, and diagonal checks, which also take O, size, time. Together, this makes the complexity of is_magic O, size, for a single square. Since there are n size plus 1 asterisk, n size plus 1 asterisk asterisk possible subgrids for a given size, the total cost for checking all subgrids of this size is O, m size plus 1 asterisk, n size plus 1 asterisk size, asterisk asterisk. When we sum this cost across all square sizes, from the largest down to the smallest, we find that the total time complexity is dominated by O, m asterisk n asterisk min, m, n, asterisk asterisk, as this accounts for all the nested loops and checks involved. The space complexity of the solution is O, m asterisk n, asterisk asterisk, and this is primarily due to the storage of prefix sum arrays. Specifically, the row_prefix array requires O, m asterisk, n plus 1 asterisk asterisk space, and the col_prefix array requires O, n asterisk, m plus 1 asterisk asterisk space. Together, these add up to O, m asterisk n, asterisk asterisk. Beyond these arrays, the is_magic function uses only a small amount of additional space for variables such as diag_sum and anti_diag_sum, which are constant in size and contribute O, 1. Therefore, the space requirement is dominated by the prefix sum arrays, resulting in an overall complexity of O, m asterisk n, asterisk asterisk. To understand the efficiency of this solution, let's compare it with a naive approach. A naive solution would recalculate row, column, and diagonal sums for every square subgrid without using prefix sums. This would result in a time complexity of O, m asterisk n asterisk min, m, n, caret 2, asterisk asterisk, as each magic square check would take O, size caret 2, for a subgrid of size x size. In contrast, our optimized solution improves this to O, m asterisk n asterisk min, m, n, asterisk asterisk by pre-computing prefix sums, which reduces the cost of row and column checks to O, 1. The improvement comes from reducing redundant calculations and leveraging pre-computed data. Mathematically, the dominant term arises from the triple nested loops that iterate over square sizes, starting positions, and the is_magic checks. Summing up the costs across all sizes simplifies to O, m asterisk n asterisk min, m, n, asterisk asterisk. Similarly, the space complexity is driven by the storage of prefix sums, scaling linearly with the grid size, resulting in O, m asterisk n, asterisk asterisk. One common mistake when working on this problem is not pre-computing prefix sums. If you calculate row, column, and diagonal sums directly for each square, you end up with a highly inefficient solution. This is because it involves O, k squared, operations for each kx square, which, when applied across the entire grid, results in a time complexity of O, n cubed asterisk m cubed. To address this, you should use prefix sums. By pre-computing sums for rows, columns, and diagonals, you can calculate the sum of any subgrid in constant time, making the solution much more efficient. Another frequent issue is neglecting edge cases, such as grids that are very small, like 1 by 1 or 1xn. These cases often require special handling, as your solution might make incorrect assumptions about the presence of larger squares. Adding explicit checks or assertions for edge cases ensures your code handles these scenarios correctly. Lastly, improper diagonal sum calculations are a common source of errors. This typically happens due to mistakes in indexing or formulas, especially for larger grids. To avoid this, it's important to carefully verify the index calculations for both main and anti-diagonals, and to test thoroughly with various grid sizes and configurations. Another mistake to watch out for is assuming that all kxk squares in the grid are valid magic squares without explicitly verifying them. This can lead to incorrect results because the condition that row, column, and diagonal sums must all be equal doesn't hold for all squares. To fix this, you need to explicitly check these conditions for every square you consider. Additionally, inefficient pruning can significantly slow down your solution. If you're checking all possible square sizes without stopping early, you're wasting valuable time. A better approach is to iterate from the largest possible square size down to the smallest. By doing this, you can stop as soon as you identify the largest valid square, saving time and computational resources. In an interview setting, there are a few key insights to keep in mind when solving problems like this. First, mastering prefix sums is critical. They're not just useful for optimizing this problem, they're a fundamental technique for efficiently handling 2D subgrid queries in general. Pre-computing row, column, and diagonal sums allows you to answer some queries in constant time, which is a huge optimization. Second, always be aware of edge cases. Interviewers love to test non-standard scenarios, such as grids where the dimensions aren't equal, or minimal grids like 1x1 or 1xn. Validating these edge cases demonstrates thoroughness in your approach. Iterative optimization is another important skill. Start with a brute force solution to demonstrate that you understand the problem, then explain how you can optimize it using prefix sums and pruning techniques. Diagonal indexing is a common area where candidates stumble, so make sure you can clearly explain how you calculate the main and anti-diagonals for any subgrid. Lastly, time complexity analysis is crucial. Be prepared to articulate the trade-offs between your brute force and optimized solutions and to justify your approach based on its computational efficiency. This problem is closely related to several other classic grid-based problems on LeetCode. For example, LeetCode 304, Range Sum Query 2D Immutable, is a great way to practice using prefix sums in two-dimensional grids. Another related problem is LeetCode 1277, Count Square Submatrices with All Ones, which involves counting squares in a grid and shares some structural similarities. LeetCode 764, Largest Plus Sign, is another optimization problem involving grids, and LeetCode 931, Minimum Falling Path Sum, focuses on working with grid diagonals. These problems can help you build a strong foundation for solving grid-based challenges. In terms of approaches, the brute force method involves checking every possible kxk square, summing rows, columns, and diagonals individually. While this approach is simple to implement, its n cubed * m cubed complexity makes it impractical for larger grids. A much better alternative is the optimized approach with prefix sums. By pre-computing sums for rows, columns, and diagonals, you can calculate the sum of any subgrid in constant time. This reduces the overall time complexity to m *n*min, mn, making it far more efficient for larger grids. However, this approach does require more complex implementation details, so it's important to practice it thoroughly. Another advanced technique for solving this problem is using binary search to find the largest valid square size. This approach combines the efficiency of prefix sums with a binary search strategy, where you test square sizes in a structured way to narrow down the largest possible size. The time complexity for this method is log min m n *m*n, which can further reduce the number of checks required for large grids. The trade-off here is that binary search introduces additional logical complexity, as you need to manage the search space and ensure that your validation checks align with the size being tested. However, for large grids, this approach can be highly effective and showcases strong algorithmic thinking. Great work! To wrap up, we summarized the problem and discussed the key techniques used to solve it, including prefix sums and iterative checks. This problem is a great example of how to approach matrix-based challenges systematically. If you enjoyed this video, don't forget to like and subscribe for more coding tutorials and insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!